So good morning and welcome back to the Thursday session of the ICTS meeting. And so Evgeny Feigin will start us off this morning, continuing lecturing about flag varieties, degenerations, and Quiver Grassmannians.
Thank you very much. So let me give a plan for today. First, I'll give one missing piece, a combinatorial piece. So combinatorics and mainly on standard monomial theory. I have to because this is in the spirit of Lakshmi Bai's work. And then I'll go to the quivers as we've seen this connection yesterday, so I'll start working on that. So quivers and representations. Then I'll describe the representation spaces or representation varieties. Here they're very simple, but still representation spaces and group actions, groups. And then I'll say define the Quiver Grassmannians. And well, most likely already tomorrow we'll get back to connection to flags. I'm unlikely be able to speak about this today, but we'll see. So first of all, let me fill one missing piece here. So just to recall notation, so we have our flag variety Fna. So n refers to the complete case, so meaning that lambda has the full support, say being rho. And so we've seen that this is the collection of spaces V1 up to Vn minus 1, such that all of them are, so say Vk is an element in Grassmannian K of Cn. And we have certain maps, projections K plus 1, Vk sitting Vk plus 1. With these maps being just projections, so projection K plus 1 and Vk plus 1 to 0 and V not equal to K plus 1 to itself. Okay. So in particular, these varieties sit inside the product of Grassmannians. And we've seen in an example that they can be somehow, well, this is a very explicit description. And in an example for n equals 3, we gave explicit relations cutting the image inside the product of Grassmannians. So these Grassmannians sit inside the product of projectivized wedge powers of Cn. So this is the standard Luker embedding, and we saw that for n equals 3, so we have one relation saying that delta 1, delta 2, 3 plus delta 3, delta 1, 2 is 0. Okay. So in general, you can also write the defining ideal. So the claim is that it's also generated by quadratic relations. These relations can be explicitly written. But for us, you remember we had this Luker algebra. And of course, we'd like to consider a similar object here. So this is again the polynomial ring in all our variables, delta I, for all possible i's over the ideal IA. Now this IA, so this is again multi-homogeneous ideal. Ideal for Fna. Okay, so let me say it again that actually, so these are all possible polynomials in Lucas variables, but we care only about multi-homogeneous part. So this Lucas algebra is the direct sum over, actually these are lambdas, but let us write m1 up to mn minus n. So sitting in z greater than 0 to the n minus 1 of the multi-homogeneous parts. So these are simply those polynomials which are linear combinations of monomials having exactly mk variables of sort corresponding to group K, right? So this Lucas NA of M is spanned by monomials. Of course, the images of the monomials having exactly mk factors the form delta I with cardinality of phi being k. Okay, so we can ask what's that, and you remember that in the classical situation, these were dual to the irreducible representations, and the theorem here says that similar statement holds in this case as well. So this Lucas NA is isomorphic to V lambda A. So please note that this is far from being obvious because so what did we do? So we somehow changed our varieties in some way. Well, this is somehow some procedure, not very simple. And then we have some defining ideal. And the claim that the dimensions of these Lucas algebras, of the components of these Lucas algebras, those dimensions are still the same. So this is what is called flatness of the degeneration. So we will see this in a more concrete way. Degeneration. Well, let me repeat that this theorem is far from being clear, far from being obvious. One needs to prove it, and then how to prove this. As I mentioned last time, there is this standard monomial theory, in particular saying that in the classical situation, you are giving your relations, you are kind of saying what are your standard monomials, and you're expressing all other monomials in terms of the standard ones. So this is the kind of philosophy of this approach by Seshadri, Lakshmi Bai, and so kind of Indian setting. Yes, thank you very much. I put here M, and lambda is the sum of mk omega k. Thank you. So yeah. Mm-hmm. Say it again, please. Yes, in the classical case, yeah. Mm-hmm. So, I mean, how to say, it's not weaker in the sense that neither the classical flag variety is contained here, nor this degenerate version is contained there. Yeah. Right, right. Huh? Yes, which is not an obvious fact. So it follows from our statement that this is the realization of the orbit closure, which does has the required dimension because the group which we act has the same dimension. So this just, but it's not obvious. So actually, I will add some details here. We'll see some other varieties of the same dimension, which are kind of not clear, not obvious, and coming from somewhere. I'll explain the source, but you are absolutely right. There is no reason why you should know from the very beginning this variety has the same dimension. But it does. And also it's irreducible. It's also not absolutely not. It is irreducible. So yeah. So what does the standard monomial theory tells us that what we need the notion what are the standard monomials. And to show you that this is not an obvious question, so you remember we discussed this notion of semi-standard tableau. Where we had the condition that we have some Young diagram and we fill it by numbers. The condition is that these numbers strictly increase downstairs and non-strictly increase from left to right. Right? These are semi-standard tableaux. But I claim that they do not provide the desired basis for the abelian case, and we can see it already here. So let's look at this relation, and let me write the semi-standard tableau corresponding to this monomial. So this semi-standard tableau is just I write 2, 3, and 1 here, and then okay, so 1, 2, 3, and 1 here, and then 1, 2, and 3 here, and there is one more guy which is missing here, which is delta 2, delta 1, 3. So this is missing. So I have to add this 1, 3, and 2. And this is semi-standard. This is not semi-standard. It is semi-standard. And this is semi. So what I want to say that this relation, right? Here we have a bad monomial, which is that one. So this is no good. Yeah, because the corresponding thing is not semi-standard, but this guy is. So in this relation, we want to get rid of this and keep this. So here, the semi-standard monomial are available still, so the same thing. But the question is, question, if for larger n, the classical semi-standard tableau provide basis for this Degenerations situation. And the answer is that no, in general. So not already for no for n larger than b. Therefore, so this kind of there should be some relation, but they are kind of too long, so I don't want to write them now. So this means that we need some another variant. So just I'm not going to give you all the details, but just what I want to do is to give another construction or another version of kind of semi-standard tableau. Which are good for, which available for both Fn and Fan. So what I want to say that there is this classical notion of standard, semi-standard tableau, and they are given by these very classical rules. But one may ask, is this kind of unique, right? So why should we take this one? And the claim is that actually for us, for our purposes, these semi-standard tableau, they don't work. So we need other replacement. And what I want to show you that there is another combinatorial construction which works in this degenerate case, PBW case, but it also works in the classical case. So this statement is that there are many, actually probably there are many variants, many versions of the semi-standard tableaus even in the classical situation. And this is one more, another one. So here is the definition. So we take a tableau. So let me call it a PBW. So of shape lambda. So this is again a Young tableau, a Young diagram. Filled with numbers from 1 to n. With the, so numbers, let me denote these numbers Tij. Okay, so satisfying the following conditions. So here I is the number of row and j is the number of column. Okay, so for example, for if n is 3 and our Young diagram is of this form, then this is T11, T12, and this is T2. Okay, so the first is the number of columns, the second number like this. Okay, so the conditions are as follows. So first of all, if so suppose that, so let us look at column number j. So we have here T1j, T2j, up to T, let me denote this number by, say, mu of j, j. So mu of j is just the height of the column, number j. Okay. So what these numbers should satisfy? So before we had this condition that they just strictly increase from top to bottom. And now the conditions are as follows. So if Tij is less or equal than mu of j, so you remember mu of j is just the number of elements in this column, then Tij is just I. Okay, so it means that if you have numbers Tij which are no larger than the length of this column, then such a number should be present exactly the place I. Okay, so for example, number 1 can show up only here, number 2 can show up only here, and number mu j can show up only here. Okay? So this is the first condition. And the second condition says that if both Ti1j and Ti2j are greater than mu j, then I1 is less than I2. So so this is sometimes called the PBW column, and I'll explain in a minute why this condition is somewhat natural. But let me give you an example first of all. So say if I have a column of height 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Then, for example, the number 4 can be found only here, and the number 2 can be found only here. And say, let me add also 5 here. And then, yeah. Oh, sorry. Thank you. Sorry. Then I1 less than I2, and of course, I wanted to put great. Sorry. Yeah. Thank you very much. So and then here I can put say 10, 9, 8. Okay. So the numbers which are larger than 6. They show up in the kind of downwards decreasing order. Okay? So this looks at the moment it looks somewhat strange, but I'll explain in a minute why this should be true. And the second condition is that for any ij with j greater than 1, there exists I1 greater or equal than I, such that T I1 j minus 1 is greater or equal than T. Okay, so this means that so if we have 2 neighboring columns, say something like that, and we take some number here, which is our Tij, then we should be able to find some guy here with I1 larger than I, which is greater or equal than. Okay. Well, at the moment, this looks like kind of ad hoc construction coming from nowhere. But first of all, let me tell you that the fact is that absolutely not a trivial fact that the number of PBW semi-standard tableau of shape lambda is equal to the number of classical semi-standard tableau of shape lambda. Of shape lambda. So this is far from being obvious. And what is more important is the following theorem that PBW semi-standard tableau provide well, basis or standard monomial basis. So basis for the standard monomial theory for both Fn and Fna. So just I'm not going to prove this, so this is not a simple task, but let me maybe just comment on why, how does this condition shows up naturally. And for that, let me get back to the, back to V omega k. So you remember the classical fundamental representations are just Verge powers of Pn. And we have a basis here, basis of the form Vi1 verge Vi. Okay. And when we were discussing this extra structure, we said that we have an high state vector, and we would like to move from this high state vector to a given vector in some number of steps. And since we are doing this PPW business, we want to minimize this number of steps. So what does it mean? It means that, okay, so we have this collection, I, is I1 to Ik, and we want to change the collection 1 to K to the collection I1, Ik. So how do we do this? So some of these guys are already inside this, so we don't have to do anything with them. And there is the remaining part, which is contains of numbers larger than K, and we have to move these guys to here. So we need, want to transform V1 verge Vk to Vi1 verge Vik in a minimal possible number of steps. So let me give you an example. So suppose, say, K is 3 and N is 8. Okay, and we have V, say, 2, verge V5, verge V7. Okay, so how we want to transform V1, verge V2, verge V3 to V2, verge V5, verge V7 in a minimal possible number of steps. So we have this V2, which is already present, so we don't touch it, but we need to transform 1, 3 to 5, 7. So how do we do this? There are, of course, two options. Either we change 1 to 7, 3 to 5, or we change 1 to 5, 3 to 7. So, well, the correct way is to change V1 to V7 and V3 to V5. So meaning that we are changing the smallest to the largest and the next smallest to the next to the largest. So correct means that actually this is some way to get basis for the spaces V lambda A. So I'm not going to talk about this, but just there's one way. So far for us, it's just some way, but it turns out to be correct way. Move the smallest to the largest. So the smallest index, the largest index, and then next to the smallest, to the next to the largest, and so on. Okay, so why am I saying that this is related to this construction? So you see, what does this picture say us? So we keep the numbers which are smaller or equal to the length of the column. So back to semi and to the PBW columns. So the condition that Tij equals to I, if Tij less or equal than mu of j, is equivalent to saying that if we have an index which is no larger than k, so k is exactly this mu j, right? So you remember the heights of the columns exactly correspond to the lambda k, to the verge power. So then it just stays at its place, so it's not moved. And then the second condition, let's say this 10 and this 9, comes from the fact that we change 1 to 10 and 3 to 9. So the smallest is changed to the largest, and so on. So the condition that Ti1, if Ti1j larger than T2 I2j. Right, so of course I didn't write it, but all the numbers, it follows, but let me write it explicitly, all the numbers Tij with given j are different, are distinct. So of course, it follows from what we wrote, but let me stress. So this condition for numbers larger than mu of j, this comes from our recipe, from the rule above, from the rule for the on. So let me repeat that, of course, there are many details missing here, and I didn't prove anything, but the message I just want to formulate here is that the classical semi-standard tableau, they are kind of not unique. So namely, probably there are also some other, but this is a very concrete construction which produces bases in our situation. This is why we needed those new tableau, but they also provide the basis for the classical. Okay, so probably that's it for combinatorics of this tableau. And so before I move to the quivers, maybe there are some questions about this. Yeah, I can say, so the idea is as follows. So we have this V omega k. So we are giving a basis. So the basis is of the form product of Fij to some powers Sij. Right, so each Fij is a change from one V to another V. So for fundamentals, we don't need, so these powers are 1 or 0, right? But anyway, this is a monomial. And we are saying that we are giving these collections Sij. So there are as many collections as there are elements in V omega k. So now let me denote these collections so that we are giving the set S omega j. Let me denote this set by S omega k. So let me write again that S omega k is a subset in Z greater or equal to 0 to the power n times n minus 1 over 2. Right, so each element here is a collection of Sijs, and the number of these pairs Sijs is exactly how many Ijs do we have. Now I want to get a basis for V lambda A. So I want to get a monomial basis. And then the claim that if we choose this S omega k using the rule I wrote, at smallest to largest and so on, then we can just we take S of the sum over k from 1 to n minus 1 sum, mk S omega k. So what did I write here? So this S omega k is a subset in this set. And then I can consider Minkowski sums. So meaning that if I have two subsets here, I can sum them up just by obvious sum by coordinates. So these are Minkowski sums of subsets. And then the claim that this is going to be the answer for this guy. So in particular, if I'm making the choice I described there, then the number of elements in this Minkowski sum is going to be exactly the dimension of V lambda, and it's going to provide the basis for this V lambda. It doesn't. No, it doesn't work. So this is the reason why. Yeah. Mm-hmm. I don't know a very simple thing, a very simple recipe how to produce a semi-standard PBW tableau from a semi-standard classical tableau. So there, I don't know. Sorry? I don't know bijective. So you're saying that for this, so we take a tableau with no repeating indices at all, or what? But I'm not sure if it has some concrete meaning here. So right, but I mean, so the kind of the question is that if you start with a classical semi-standard tableau, how to produce some PBW semi-standard tableau for anyone, right? And I don't know this concrete recipe. So there are some kind of indirect way to show that, but no, I don't know combinatorial. Some more questions? So okay, if not, so let us then change the topic so you can for a while forget about everything which we've discussed before. We are passing to the world of quivers. So we've seen quivers already several times. It is just a collection, so Q. This is pair Q0 and Q1. So Q0 is the set of vertices. And Q1 is the set of arrows. So for each arrow, there is a source and a target. So alpha in Q1. So there's a source of alpha and the target of alpha, and this is just a directed graph. Well, the main example for us is going to be Q equioriented type A quiver. Which is just of the form. They have several vertices and the arrows pointing from one to another in one direction. So to each quiver, one attaches a path algebra, which is an associative algebra. So a path in Q is just a path. So meaning that you take several arrows starting such that the source of the next one is the target of the previous ones. I'll say alpha 1, alpha s minus 1, alpha s. So this is a path. Okay, and we have a path algebra PQ, so associative. Algebra spanned by elements labeled by S, say elements say P, where P is the path. Okay, and then if you want to multiply these two elements, you just concatenate the path. So if you can, right? If you cannot, this is just 0. So in particular, so for example, there are so-called lazy paths. Length 0. EI, which correspond to the path of length 0 starting and ending at I. At the vertex I from U. Okay, so for each vertex you have a lazy path, and if you sum them up, then you just get the unit in the algebra. So the unit in Q is the sum of EI over I from 0. So you can easily see this, right? Because if you have any path and you try to multiply this unit and the element corresponding to the path, so you get exactly the same path, right? Because it depends on which side you multiply, but still there is only a single lazy path, which is kind of good for that. So this is just the general setup for quivers. Now, what is the representation of a quiver? So a representation of Q is a collection Mi, I from U0 of vector spaces, and a collection M alpha from Q1 of linear maps where M alpha is a linear map from the source of alpha to the target. Okay, so just for each vector space you give for each vertex you give a vector space, and for each arrow you give a map. So actually we saw already 2 examples of representations. So example. So suppose Q is just A2 and M1 equals M2 is E3. So we have 2 3-dimensional representations. So 3-dimensional spaces. And we also need a map by here. So this is actually M alpha. And then we saw that, for example, for our purposes, we needed M alpha identity or M alpha of rank. Okay, so these were just examples of representations of the A2 quiver. So the dimension of M, just the collection of dimensions, Mi. So this is a vector inside z greater than 0 to u0. So for any vertex, you attach a number, it's just a dimension of this space. And so clearly, you can somehow do the whole representation theory business, so meaning that you can define sub-representation, quotient representations, homomorphisms. So either you just work with the path algebra. So this associative algebra, you just say that these are corresponding objects for the algebra. But we can also do it in a purely quiver language. So meaning that, so say a sub-representation is a collection subspaces Ni inside Mi for each vertex I, such that if you take M alpha and apply it to n source of alpha, you arrive at some vertex vector from S star. Okay, so this is the simplest thing you can imagine. And so since we define what are sub-representations, we can say that the notion of irreducible representation and then decomposable representation. So the irreducible representations are very easy to describe. So say, for example, irreducible representations. So they are Si, I from 0, and they are very simple. So you just say that Si has one-dimensional space at vertex I and 0 at other vertices. Okay, so of course the maps are trivial because these are maps from 0 to 0 or from one dimension to 0 dimension, so no choice here. And so the indecomposables are more complicated, so I'm not going to give kind of full description. There's no way to do this in general, but let me give you an example. Indecomposable modules for equioriented type A. So our quiver is just this one. So we have vertices 1 to n minus 1 n. So there are n vertices, and each representation. So to define representation, we have to say what are the spaces, and so the indecomposables are as denoted by U, I, J, where I and J are from 1 to n, and they look like following. So we have several zeros, and then several one-dimensional spaces. Then again, several zeros up to the n. And this is position I, and this is position J, and these are the identity maps. Okay, so for the claim is that indecomposable representations are labeled by pairs I less or equal than J between 1 and n. And this is exactly the picture for such a representation. So you can see that they are kind of parallel or in bijection with positive roots of SLM plus 1, and this is the general Gabriel theorem, so which holds for any Dynkin quiver. But here, this is very, very explicit description which we have. This is what we need, and of course there are many representations. So every representation is the sum of indecomposables. We'll need some particular classes. So let me give one more example. So we define Pi to be the representation of the form U I n, and II be the representation of U1I. Okay, so it means that they correspond to the segment which either ends at the last vertex or starts with the first vertex. And the reason for these P and I's is that this is a projective module, it's injective module, and these are all indecomposable projective and injective. So if you're not comfortable with this projective injective business, just don't have to care. So these are just very concrete modules we're going to need later. Good. So now we have these quivers, the representations. Now let us try to explain what are all possible representations. So what are what are all possible representations of Q of fixed dimension. So what do we need to say? So what do we need to fix? So we have D, which is a collection of numbers, Di, I from U0. And this is an element in Z greater or equal to 0 to U0. So to each vertex, we attach a number. This is going to be the dimension of our representation. So in order to define the representation, since our dimensions are already fixed, we have to say what are the maps. Let me denote it by rep D. So sometimes we put Q here, but if the quiver is kind of fixed, so sometimes we omit it. So this is just the direct sum overall alpha in Q1. And these are home spaces from C, D source of alpha to C, D target. Okay, so actually this is absolutely obvious thing here. So in order to define a representation, so we have to define spaces and maps. So the spaces are fixed because the dimensions are fixed. Now the only thing we need to do is to define the home spaces here. So this is called the representation space, and we know that this is just the affine space of a dimension which is easily computed, right? So just the product of ds alpha, dt alpha, overall alpha from Q. And of course, this representation space is much simpler than for general associative algebras, because we've seen that for associative algebras, you also need to quotient out by some ideal, right? And then you need some relations, but we don't have, so it's just, okay. So we do know that some representations of U are isomorphic. So meaning that, so we have, so the, say, collection Mi and collection Mi tilde. So an isomorphism, for this, we need some map, say Gi, from Mi to Mi tilde. So an isomorphism, but they have to be compatible with the maps. So meaning that if we have an alpha from Mi to J, have Gj here to Mj tilde. So this diagram has to be commutative. So this is an isomorphism between M and M tilde. It's natural to introduce the group action on this representation space, which takes care of these isomorphism classes. Let G be the product of GL di, I from U0. So the group is kind of very concrete. So you take just the product of general linear groups corresponding to the vertices. And then G acts on this representation space just simply by base changes. So meaning that, so suppose we have G, which is a collection of Gi over I from U0. So this is an element in G. And then we also have an element in our representation space, which is just a collection of linear maps. So we have F alpha, alpha from Q1. So this is an element in our representation space. And then what we get is just we compose this section, and we get G F alpha and then G, and we put here the source of alpha, the target of alpha. Here the source of alpha, and we have to take the inverse of alpha from one. Okay. So just the base change, which corresponds to this picture here. And then the simple observation is that the orbits of this action correspond to the isomorphism classes of U modules of dimension. Okay. So let me give you a very concrete example of such picture. Namely, we take our simplest A2 quiver, for example. So Q is A2. So D is D1, D2. Okay, and so our representation space is simply home space from CD1 to CD2. Okay, and then what are the isomorphic representations? So what are the orbits? So the orbits are parameterized by rank of this map. Okay, so it means that number of orbits is exactly the number of possible ranks. So it's very kind of linear algebra statement. So of course, there might be larger orbits or smaller orbits. So let me make it precise. So we say that a representation M degenerates to N, where both M and N are from this space rep D of Q. So if the orbit of our group G, the closure, contains N. Okay, so it means that you have one representation, another representation, and then you take the orbit of this M, so meaning that you consider all possible representations isomorphic to M, and then, well, N could be in this orbit or not, so we don't know, but it might be the case that this N sits inside the closure. Okay, so then we say that we kind of degenerate. So let me give you an immediate example. Makes sense, right? So N is not isomorphic. So an example is, so again, let us stay in the same situation. Q is A2, and then let Z be 3, 3. Just two three-dimensional spaces. There is some reason to put 3 here because this corresponds to SL3 and this will be 3 or SL3. And then there is an orbit, so it can take M, the form P3, and then here just identity map, and then P3. And this is the kind of largest orbit. So if you take a kind of generic map, it's going to be invertible, maximum rank. And then we can take another M, let me denote by M tilde, which is E3 to T3 of rank 2. Okay, then you can degenerate this to here, from here to here in the simplest possible way. Just put diagonal and then just one number change from non-zero to zero. Okay, so this is for the orbit, and now you can ask what is the structure of this degeneration, and there is the theorem which says that for U Lincoln, there exists a unique maximal orbit, unique open dense orbit in gravity. So it means that we see here that, so if we take a generic map, it's going to be just an isomorphism. So this is a kind of generic situation. So the claim is that the same thing holds in general, or in general for Dynkin quivers. So there is a kind of generic situation where, so kind of you pick a generic point, it's going to be from this orbit, and all other points, all other orbits are degenerations. So any m from this unique orbit degenerates to any other. So any point can be obtained as generation of this generic thing. And so let me stop here, and then next time we'll discuss the Quiver Grassmannians and relate this to this thing. Thank you.
No, thank you, Evgeny. Any questions for speaker?
Assuming anything about the quiver here, I mean.
So here Q is Dynkin.
Oh, Dynkin.
Dynkin quiver, yeah. Of course, it's not true in general. Wonderful. Yeah. So there are finitely many orbits and one then.
Semi-standard tableau that you told me. Any of that's compatible with the Demuzur modules?
I don't know, but I think not in general. So again, maybe Gislan had some cases where they are compatible, but actually I don't remember what if he considers this Schubert case. But so I think there are some cases, special cases, some avoiding some patterns where it is compatible, but I don't know, and I'm not sure it's studied actually. And I think that in general it's.
How do you even define given a W? How do you know which ones to do?
Say it again?
No. Continuing his question.
Yeah.
So from your answer, it seems like given a W, you know which ones.
I don't know, but I'm saying that Gislan Fourier, he had some papers where he explained that for some de Mazur modules, the bases, at least, are kind of this FFLV basis. I didn't say what's that, but this is what follows our discussion on this V omega K. So these PBW bases, they produce bases in de Mazur modules. So I'm just saying that maybe in these situations where these FFLV bases work, also this PBW semi-standard tableau work. But this is just a conjecture, I'm not stating.
Any further questions? So, well, thank you again, Evgeny.